So now we are going to sketch a curve based on the following guidelines. So what are the guidelines? So the guidelines are as follows. So you want to basically first find out domain of a function. And so where does the domain of the function? So generally the problem occurs when, so if you have a rational function, denominator should not be 0. Even otherwise as well, if you're dividing, if your function has a ratio of two functions, the denominator should not be 0. Negative square roots are not allowed, for example. Yeah, then negative values in ln x. So if you're looking at ln x or square root of x, you need what? X greater than 0. Okay. So the first thing we should check is the domain of the function. Okay. So we will go through the guidelines by following a problem. So we have a problem here. So first of all, again, according to our guidelines, we need first the domain of the function. So domain of the function, I'll use t of f is all real numbers, except now in this case, we have a fraction. The numerator is defined at every value. The denominator is also defined at every value. So the function is defined everywhere except when the denominator is becoming 0 and denominator becomes 0 at 1. So domain is all real numbers except 1. The next thing we should do is look for the intercepts. So x-intercepts, for x-intercept, we should put y equals to 0 and solve for x. For y-intercept, we should put x equals to 0 and solve for y. So let's look at that. So 2 x-intercept. So for x-intercept, solve for f of x equals to 0, which gives us 2 plus x minus x squared upon x minus 1 square equals to 0. This gives us the numerator is 0, which means x plus 1 times x minus 2 equals to 0. And we have to check that the denominator is not 0 at that point. So this is what we need to solve. Okay, so this will give us x equals to minus 1 or x equals to 2. And we need to check, does it makes denominator 0? No. So these are the x-intercepts, x equals to 1 or x equals to 2. Now for y-intercept, solve for x equals to 0 or find f of 0. In this case, we get f of 0 equals to, when you put 0, you get 2 over minus 1 square, which is 2. So y-intercept is 2. Now, next thing we should discuss is about symmetry. So even function or odd function. So for example, let's take, what is an even function? Even function is when f of minus x equals to f of x for all x in the domain. And what about odd functions? So for odd functions, we have f of minus x equals to minus f of x cubed. Sorry, minus f of x. So an example is f of x equals to x squared upon x squared plus 1. So if you look at this guy, when you're drawing this graph, you just need to focus on one side because it's symmetric around y-axis. So when you're drawing this, this is 1. So this is how the graph looks like. So in principle, you just have to focus on only on one side to draw using reflection on the other side. Now, odd functions are symmetric around origin. Say, for example, f of x equals to x cube is an odd function, is odd. So in that case, if you have drawn on one side like that, you just reflect it in the origin and you get the answer. Now, next kind of symmetries which exist are in the periodic functions like sine x, cosine x, which are periodic in 2 pi, right? Period is 2 pi. Or for that matter, tan x, where period is pi. Okay, so they are periodic functions. So now in this case, there is no symmetry, right? Why is that? Because of the domain. The domain is in the way that there's no symmetry. So no symmetry. Because f of -1 is defined, but f of -1, that is f of 1, is not defined, right? So clearly none of these will apply. So we have no symmetry due to domain of the, because of the domain of the function. Now, what is the so now we need to talk about the asymptote. So what are horizontal asymptotes? Recall, if limit at x goes to infinity of f of x is L, then we have y equals to L is a horizontal asymptote. Similarly, limit at x goes to minus infinity of f of x is L, then y equals to L is a horizontal asymptote. So now in this case, we need to compute. So for horizontal asymptote, compute limit as x goes to infinity of f of x. So which is what? Limit as x goes to infinity of 2 plus x minus x squared divided by x minus 1 square. And that, when you divide both top and bottom by x square, you will see that that is 1. And not only that, you have to check for both. Limit as x goes to minus infinity of 2 plus, because there could be two different asymptotes on both sides, or there could be an asymptote on one side, but not on the other side, right? So we have to check whether it approaches the, what are the asymptotes on both sides as x approaches to infinity and x approaches to minus infinity. So we need to check both of these, all right? We need to check both of these, yeah? So let me write that as a reminder. So we should check as x goes to plus or minus infinity both. So therefore we get, therefore y equals to -1 is a horizontal asymptote. Okay. Right. So now the question is, suppose you have an asymptote like that, y equals to 1. The question is, does it approaches from top like that to 1, or does it approaches from bottom to 1? Yeah, so we need to decide on that as well, right? So then the question is, does f of x approach the asymptote, the horizontal asymptote, from above or below? So for that, we have to look at the sine of, so look at what? Look at f of x minus of minus 1 and see what happens limit as x goes to infinity of this, plus or minus infinity of this, right? So let's see what is f of x minus of minus 1. So we have f of x minus of minus 1 is going to be 2 plus x minus x square upon x minus 1 square plus 1. That is going to be 3 minus x upon x minus 1 square. So instead of basically, you can draw the sine diagram instead of looking at the limit. So sine diagram for f of x minus of minus 1, because it will tell you if it is positive, then it will approach from. So if this is positive, so if this is positive, so if this is positive, if positive, as x approaches infinity, then what happens? If this is positive, that means f of x is bigger than y equals to minus 1. Then f of x approaches from top, from above. And if it is negative, as x goes to infinity, then f of x approaches from below. Yeah, so this is what we want to do, right? So when you simplify this, this is what we get. Let's draw the sine diagram. So sine diagram will tell you right away. You don't have to see as x goes to infinity here. It will tell you what is happening. So what is the 0 of top is 3. 0 of bottom is minus 1. So now let's see. So when x is 0, so let's look at here. So minus 1 should be on the other side. My bad. So let's look at minus something which is, so again, the sign will not change because the denominator is always a square. So let's just worry about the numerator. So before 3, it has, so if x is negative, then 3 minus x. So let's take x equals to 0, right? So here you'll get positive, and here you'll get, say x equals to 4, it's negative. So it means what? So as x approaches infinity, f of x approaches is y equals to minus 1 from, because this is negative in this part here, it will basically approach from below. Whereas as x goes to negative infinity, f of x approaches y equals to negative 1 from, in this part it is positive, so above. So this is a profiling of horizontal asymptote. The next thing we want to discuss is the vertical asymptote. So for vertical asymptote, we need to do, if x equals to a is a vertical asymptote if one of the following is true, as x goes to a plus f of x is infinity, or x goes to a minus f of x is infinity, or x goes to a plus f of x is minus infinity. So either of these things happen, then we'll get a vertical asymptote. So now we have taken care of the horizontal asymptote. Now we want to discuss about vertical asymptote. So x equals to a is a vertical asymptote if at least one of these four things are true. So let's talk about 6 vertical asymptote. So let me write down the f of x again. So f of x is this function here, 2 plus x minus x squared upon x minus 1 square. So now notice that things are changing around 1, right? Everywhere else, the limit cannot be. So except 1, the function is continuous because rational functions are continuous on their domain. So they will never be infinity. So only at 1, there is a problem. So 1 could be a potential candidate. So let's see. What is limit as x goes to 1? So generally, we should go from 1 plus and 1 minus to see what do we get. So 1 plus. So let's look at 1 plus 2 plus x minus x squared upon x minus 1 square. Now the denominator is always positive, right? This is always positive. The numerator is, if you're close to 1, this is positive. So this is positive close to 1. So this is going to be, so positive or positive, so this is going to be plus infinity. Not only that, we have limit as x goes to 1 minus f of x is also plus infinity. Yeah. So what does it mean? It means that it approaches, so we can say f of x approaches positive infinity. So f of x approaches positive infinity from both left and right of a, from left and right of a, which is 1 here. 1. Yeah. So when you're drawing this, you'll get that at 1, you will have from this side of 1 you're approaching, then it goes to infinity. From other side of 1 also it goes to infinity. So this is what it means, right? So we have to. So now what is the other thing? So we'll come to the slant asymptote. So slant asymptote usually exists when basically, so what is a slant asymptote? So slant asymptote looks like that. So you will have a line y equals to mx plus b, to which your graph comes very close to. Yeah, so this is what happens when you have a slant asymptote. Now, generally that happens when degree of denominator is equal to degree of numerator. So degree of denominator plus 1 equals to degree of numerator. So when you do the long division, you have a linear factor out. We'll come to this in a moment. In this case, we have degree of numerator and denominator are same. So no slant asymptote, right? Degree of numerator is 2, degree of denominator is also 2. So no slant asymptotes here. Now we want to talk about interval of increase and decrease. So for that, we need to know what is the first and second derivative. So for increase and decrease, we need to know the first derivative. So f prime x, so I'll provide you with f prime x right away. So f prime x is x minus 5 over x minus 1 cube. And if we compute f double prime x, that is going to be 14 minus 2x divided by x minus 1 to the power 4. Okay. So let's proceed on this problem now. So interval of increase and decrease, right? So for that, we need to find out the derivative critical number. So interval of increase and decrease and local maximum and local minimum, right? So that all can be taken care by looking at the first derivative. So f prime x equals to x minus 5 upon, so it's x minus 5 upon x minus 1 cube. Now we have f prime x equals to 0 at x equals to 5 and x does not exist at x equals to what, when the denominator 1. So note that, so note, so I'll write the note in the red. You don't need to write it when you're writing the solution, but it's important to note that note 1 is not a critical number. But still plays an important role in shape of the graph. Why is 1 not a critical number? Because if you look at f is not defined at 1, right? The function f is not defined at 1. So therefore, it's not a critical number. So what we'll do is we'll do Sine diagram for f prime x. So that amounts to basically drawing a line and marking where the numerator becomes 0, which is at 5, where denominator becomes 0 at 1. So now let's check the sign. So here, if you want, you can write infinity on top and 0 here just to see what is happening, but you don't need to do that. Now let's check a sign here. So let's take anything here. So it's 0. When you put 0 in the denominator, you get 0 minus 1 cube, which is 0. And here you'll get, 0 minus 1 cube, which is negative, and on top 0 minus 5 is negative. So negative divided by negative makes it positive. Similarly, let's take 2 here. So when you put 2, you will see that the numerator is negative, but denominator is positive. So here you will have negative. Similarly, let's take 6 in this interval here. So when you take 6, numerator is positive, denominator is positive. So here it's positive. So that means what? F. So what does it mean for f of x? It's increasing, decreasing, increasing. So we get what? Therefore we get, so what kind of point is 5 then? F5 is, f of 5 is local min. So let's write that down. F of 5 is local min. What test are we using? First derivative test. And what about this point? This point is not a local extrema, right? It's not local extrema. Why? since not a critical point, since not critical. So we have done basically interval of increase and decrease and what? And local extremum. Now, the next thing we want to discuss is the concavity, right? Where it's concave up, concavity, and inflection point. Yeah, so we should compute f of 5. So when you put 5 here in this equation, so f of 5 is, so f of 5, which is equal to minus 9 over 8. Okay, so that has to be computed as well. So concavity and inflection point. So for that, we need to take the second derivative. So second derivative of x is going to be, which is already given to us, minus 12x 2x upon x minus 1 to the power 4. So note that f double prime x equals to 0 when x equals to 14 over 2, which is 7, and f double prime x does not exist when x equals to 1. Yeah. So now again, we need to draw the Sine diagram. So Sine diagram for f double prime of x. So for that, what you do, you draw a straight line, mark where the numerator is becoming 0, which is at 7, denominator is 1. So we get at 1, before 1, let's take a value, say 0. So you'll see that denominator is always 0, so it will not participate in changing the sign. It's only numerator. So you'll see that before, at 0, this is positive, again positive, and here it's negative. So it's concave up, and concave down. Note that even if the sign, it changes from concave up to concave down across 1, it won't be an inflection point, right? So here we get inflection point. So this gives us inflection point at 7. This is concave up, concave down, sorry, concave up again here, and concave up. My bad, concave down, right? Concave up, and concave down. So what is the inflection point? Inflection point is 7 comma f of 7. So note that the function should be defined at the inflection point. So 7 comma f of 7 is minus 10 over 9. So this is the inflection point. Okay. So now we are ready to draw. We are ready to draw the graph of the function. We will draw now by basically taking the points. So what are the important points? So let's start with the first. X-intercept is minus 1 or 2. So x-intercept is minus 1 or 2. So just say so these are the x-intercepts. Let's mark them. Minus 1 or 2. Okay. Now what about y-intercept? So y-intercept is 2. So f of 0 is 2. So that means it will cut 1, 2. So this is your y-intercept. Okay. Now, what are the other important things? So next we discussed about no symmetry. We discussed horizontal asymptote, which is x equals to -1, and vertical asymptote, which was x equals to 1. So let's draw. So y equals to -1 is your horizontal asymptote. So y equals to -1 is a horizontal asymptote. So let's just draw that. Let's draw it with a different color pen. So to indicate, okay, so this is your horizontal asymptote and your vertical asymptote is x equals to 1. Right. So now we'll draw the whole, so instead of drawing how it approaches to asymptote, we should fill in the other information. What is the other information? The other information is local extrema. So what is local extrema? So at 5, we have -9/8. So -9/8 is slightly less than, so we have -9/8 is going to be here. So -9/8, so this value is -9/8. And where do we get that value? We get that value at 5. So at 5, so 1, 2, 3, 4, 5. At 5, we have -9/8. Now, what about, so that's only one, we have only one local extrema, which is the local minimum. And what about the concavity? So we have inflection point at 7 f of 7, and so f7 f of 7, so that is 7 minus 10 by 9. So 5, 6, 7. So let me mark with this point here. Now 10 by 9 is slightly above. So 10 by 9 is slightly above -9 by 8. So minus 10 by 9 is slightly above. Now with this set of information, we are ready to draw the graph. So let's break it piece by piece and try to investigate what is happening on this side first. So before -1, what is happening to the function? So well, function is increasing all the way until 1. So before -1, and so function is increasing all the way to 1, and also it's concave up all the way to 1. So I'm patching up this information with this information here. Okay, so let's draw those things. So before -1, the function is increasing and it's concave up. Now we have to see, so before up to 1, not -1. Up to 1, the function is increasing. Again, 1, it's increasing and it's also concave up. Now we have to see how does it interact with asymptote. So before -1, as x goes to infinity, is approaching to the horizontal asymptote from above, and it's approaching vertical asymptote to infinity. That means in this way. So let's draw this piece of information all together at once. So it's concave up. In this part, it's concave up, increasing, all right? And not only just this part, all the way until here. So let's just draw this. So concave up and above the asymptote, so concave up. So let's just draw that. concave up, concave up, comes to cut the x-axis at the intercept. Then goes, cuts the y-axis at y-intercept, still concave up, and keeps on increasing. So this is how the shape looks like. So let's smoothen this a bit. So this is the first piece of information. Now, for the other part, from 1 onwards, it's still concave up until 7. So we'll concentrate until 7. And what about the function? Is it increasing or decreasing? It's decreasing until 5. So let's concentrate from 1 to 5, which is common of this. So 1 to 5, the function is decreasing. Again, the asymptote was again going here, it was infinity. So it's decreasing, comes down, cuts the intercept, decreasing in concave, still concave up way. Cuts the intercept. Then goes down all the way until 5. Okay, sorry. It has reached local minima. 5 is a local minima. So after 5, it starts increasing, as you can see here, right? Increasing in what way? Until 7, it's concave up. So it increases up to 7 in concave up way. Till 7, it is increasing in concave up way. And after 7, what happens? It changes to concave down and approaches the asymptote from where? From below. So it approaches the asymptote, still approaches the asymptote, but from below in concave downward. So this is how the graph looks like. So we should mark these points. These points are, so I should say inflection point, local min, then horizontal asymptote, this is vertical asymptote, this is y-intercept, these are x-intercept, and this is also x-intercept. So we have labeled all the points, and we should also give them the coordinate. So this is going to be 7 comma minus 10 by 9. This point is 5 comma 9 by 8. So 5 comma minus 9 by 8. This is minus 1 comma 0. This is 2 comma 0. Sorry, 0 comma 2. This is 2 comma 0. Okay, so all the points are marked, and horizontal asymptote y equals to -1, vertical asymptote x equals to 1. In this example, we are going to just focus on asymptotes and see what kind of asymptotes we have. So let's ask questions. Horizontal asymptote. So are there any horizontal asymptotes? So for that, we need to check limit as x goes to infinity of f of x. You will see that the numerator is rushing to infinity faster than the denominator. So you'll see that when you compute this, you get infinity limit as x goes to minus infinity of f of x is also minus infinity. Since it's not going to any fixed number, right? So no horizontal. So no horizontal asymptotes. Now, what about the vertical asymptotes? So first of all, check the domain restriction. So you see that domain is not 1. So domain is all real numbers except 1. So there's a possibility at 1. So limit as x goes to 1 plus of x square plus x minus 1 upon x minus 1. Now the top is fixed. When x goes to 1, you'll see that the top goes to 2. So top is roughly 1. The denominator goes to 0 from right. So it goes to 0 plus. This is going to be infinity. Limit as x goes to 1 minus. Same thing for top goes to 1, but the denominator goes with 0 to 0 with a minus sign. So we get what? So x equals to 1 is a vertical asymptote. And what goes to infinity from the right because of this part here, right? 0 right of 1 and minus infinity from left. So vertical asymptote. So slant asymptotes. So what about slant asymptotes? So is there a slant line which is neither vertical nor horizontal, which is an asymptote? And the answer is yes. Why? Because degree of denominator is 1 plus degree of numerator. So since degree of numerator equals to degree of denominator plus 1. Let's see how does that help. So how do we find out to be slant asymptote? How do we find out what is the equation of slant asymptote? Use long division. So we have x squared plus x minus 1 upon x minus 1. So let's divide and see what do we get. So we have x squared plus x minus 1. So if you want to divide this, how many times does first one goes in x squared? X times. So we have x squared minus x. So subtract, we'll see that this will change to 2x. This will be minus 1. And then how many times does that goes? X and 2x, so plus 2. Minus 2, and when you subtract, you get 1. So therefore, you can write x squared plus x minus 1 upon x minus 1 is going to be x plus 2 plus 1 upon x minus 2. So this means what? This means if you write your f of x minus x plus 2 and you take limit as x goes to infinity of this will be simply limit as x goes to infinity of 1 upon x minus 2. I brought it on the other side, which is going to be, as x goes to infinity, you get what? This is 0. So this means as x goes to infinity, your f of x gets very close to x minus 2. Yeah, you should check on both sides actually. So similarly, x goes to minus infinity of f of x minus x plus 2 is going to be 0 as well. So therefore, line y equals to x plus 2 is a slant asymptote. Now you should see, we should try to understand what does it really mean. It means that as x goes to infinity or minus infinity, f of x and x plus 2, they become very close to each other. And that's why we get a slant asymptote. So if you draw, in fact, you will see the graph of this function looks like the following. So if you look at the graph, sorry. So we'll have line x equals to y equals to x plus 2. And let's just draw this. So, okay. So this is the slant asymptote, and you can see your function will be your function looks so. Your vertical asymptote is x equals to 1. So at x equals to 1. So x equals to 1 is somewhere here. And when you draw the graph, this is roughly how the graph looks like. Extend this as well. So this is how the shape of the graph looks like with the slant asymptote.